In this video module, we will be looking at a customer arrival process, and in particular what we'd like to do is a visual assessment of the stationarity of the data. So let's talk a little bit about that. First of all, the module objectives of what I want you to get out of this video module. I want you to understand the issue. When we talk about stationarity, what does that mean and what's the data that we have in the data sets? Then I want to demonstrate some code, Python code, that does two things. Basically reads and processes the data sets into the format that we'd like to have. And then two, generate some visualizations that an analyst would use to make this stationarity decision or to understand the stationarity of the data. Notice I say that you can't determine this from the visualizations. The visualizations are simply one input that we would have to answer the overall problem. If you're interested in the more detailed analysis that goes beyond the visualization, then simulation is the class for you to take, and I would suggest that you do that because it turns out that this is a very interesting topic. To start off, let's take a look at the environment that we are talking about. So what I have here is an animation from a simulation model of a food truck. And in this model you can see that we have customers that arrive to the food truck, and then they would be served whatever they ordered, and then they would depart. So we have a fairly standard single server queuing system that we're modeling. What we're interested in here is, in order to create this model, I need to be able to characterize this customer arrival process. In other words, I need to know when customers arrive, overall the rate they arrive, the time between successive arrivals, because those are the things that determine the queuing and the number of resources that I need to support the model or to support the food truck. So in order to make this assessment, we have a set of data files. So we have a set of observations. Let me just show you this here. So we have 30 individual data files, and so I've labeled these day A 1 through 10, day B 1 through 10, and day C 1 through 10. And I'm going to talk about what A, B, and C are here in just a second, but for now just concentrate on these numbers. And so you can think of these for A, for example, as 10 days worth of observations. And what the observations that we have are the actual customer arrival time in hours. So this says from the start of the day, from when the food truck opened, the first customer arrived at 0.015 hours after they opened. The second customer arrived at 0.020 after they opened, and the third customer at 0.148, and so on. So this is just the time of arrival during that day. And so what we want to be able to compute from this, we want to be able to compute the time between arrivals, which is sometimes called the inner arrival time, or IAT. And so we can easily make this computation. For the first customer, it's simply the arrival time. And then for the second customer's inner arrival times, it's simply the arrival time of that customer minus the arrival time of the previous customer. And so if you, in Excel anyway, if you just copy that formula down and so on, you can get the inner arrival times. And so we basically are interested in these two streams of information, as we will see when we get to our Jupyter Notebook. So once again, the data that you have for 3 different scenarios, 10 different days of data, and the data that we have are the arrival times. And so I need to be able to read those arrival times and then compute the inner arrival times for each day. That's the information that we want to deal with. So now the question is, well, what do we mean by stationary or stationarity? And so I pulled the definition from Wikipedia. It says a stationary process is a stochastic process whose unconditional joint probability distribution does not change when shifted in time. Consequently, parameters such as mean, variance also do not change. So in our context, basically what that means, if you think about the food truck, we're interested in, does that process change over time? And so you would think, when the food truck opens, are we going to see customers arrive at the same rate that they would arrive, say, at noontime or in the evening time? And so that's really what our interest in is, looking at this stationarity based on the data. And so since we have 10 individual days of data, this notion of stationarity has two different has two different facets. First of all, we need to know day to day. So I might have 10 days, which would be, think about 2 weeks. So I have 2 Mondays, 2 Wednesdays, 2 Tuesdays, and so on. I want to know, is the process stationary from day to day? In other words, are Mondays and Tuesdays and Wednesdays and Thursdays similar? The second facet is within the day, which is what I talked about earlier when we talk about when the food truck opens and at lunchtime and in the evening time and so on. So when we talk about stationarity of the data, we have both of these facets that we need to think about. So the question now becomes, well, how do I do this? So once I read it into Jupyter and all of that and process the data, what is it that I want to be able to do? And so if you think about the customer arrival rate over time, what I have here is two different examples. The one on the left is on time, and then I have YT, which would be the customer arrival rate. And so this would be a stationary arrival process where customers arrive at the rate lambda through the entire time period. On the right side is a non-stationary process where the customer rates start off small and then gradually build up and then taper off. So this is probably what you would think about, at least for a food truck that, say, serves lunch. Then it would open early, you'd have some customers, and then through the up until the lunch rush, and then taper off in the afternoon. So if you think about the context that we're looking at, we would probably expect something like this versus like this. However, the general problem of determining stationarity is goes way beyond just customer service type operations and food trucks and hospitals and so on, and into any kind of time series process. So our interest here for this video module is, how do I look at the data sets and then sort of make a visual determination of this stationarity? So now the question becomes, well, how do I do that? How do I take the data that I have, which will be a set of arrival times and a set of interarrival times, and make this determination, or make a graphic or a visual that will help me make that determination? Well, what we're going to do is we're going to create two sets of histograms. I'm going to take the arrival times, and if I think about binning these and then counting the number of observations, so if I just take a set over time here, like this set for example, and count these and then track that over time, I'm essentially going to have an estimate of these values. So if you pick any particular time, again, we can't deal with continuous time, but if I take any time range, so if I took this time range here, for example, right here, if I just counted the number of observations of arrivals that occurred within that range, then I would have an estimate of this value over that bin time. And so that's exactly what we're going to do. In addition, I said we're going to do two histograms. We're also going to do a histogram of the actual interarrival time distribution, because when we do the simulation model, this is the actual piece of information that we would really like to have, that we need to code, or we need to put that in the simulation model to generate arrivals. So again, the histogram of the arrivals is going to be our primary tool for making the stationarity assessment, and then the interarrival time distribution is just additional information that we would use to generate us or to code our simulation model. Let's go and have a look at the Jupyter notebook that does this, and so there it is right there. Let me, as usual, shift into full screen mode. And so again, we're modeling a customer arrival process, and as I say, we have a 10-day sample. We actually have 3 10-day samples, which I'll talk about that in just a second, and we're interested in making that assessment. So the first thing we're going to do is we're going to get things set up, and I'm going to use our usual tools of NumPy, Matplotlib, Pandas, and Seaborn. I'm going to set the style to Seaborn White Grid to make things look good. And then I'm going to process my data files. And so a couple of quick notes here. When you download this, make sure and check the file path, because I've put the files in a subdirectory off the normal data directory. So because I have 30 individual data files, I didn't want to clutter that up. You can when you unzip the file, you can adjust the path as necessary. So I mentioned before a couple of times that we have essentially 3 different data sets, and they're defined by A, B, or C. So 10 of the files are day 1 or day A1, day A2, and so on, day B1, day B2, and so obviously the A's represent the A data set, the B's represent the B data set, and the C's represent the C data set. So we have 10 days for each one of these three. And the three different data sets represent three different arrival processes, as we'll see. And so I'll just go ahead and tell you what the data sets are, because the objective here is to learn how to do the visualization and make the assessment. So it generally helps to know what we're looking for. Data set A is stationary data. Data set B is a non-stationary two-phase problem or two-phase data set, so there are two different arrival rates. And data set C is a non-stationary four-phase data set. And so what we're going to do is we're going to go through each one of these and see how they differ. So what we're going to do, set the number of replications here. We also have the number of bins for our histograms, and so this is something that I know. This is something in general you wouldn't know this, but I'm just going to assume that we have 8 hours worth of data. So each day from our food truck or from our customer arrivals process is 8 hours long, and so I'm going to set my histogram bins to be hour width bins. So I first read all the data in, so I created a list called all arrivals, all ARRS, and I simply read those in, assuming they're all floats. So right here I convert them to float into an individual list, and then I append that to the general list. Oops, I called that IATS, but that is not actually IATS. These are arrivals. It doesn't matter because this is just a temporary variable to accumulate the arrival times for each individual day, and it's the all arrivals where I actually store the day's worth of data. So when I finish executing this loop, this list will have 10 lists internally, each one corresponding to one day. Once I have that, I can compute the inner arrival times, just like I showed you in the, let me go ahead and execute that, just like I showed you in the Excel spreadsheet. So I create my all IATs, and then I sequentially go through and set the first value equal to that first arrival time, and then all subsequent values I just subtract the previous one. So I take arrival time of K and subtract arrival time of customer K minus 1. And so what we end up with again is a data set where I have a list with 10 individual lists. Okay, so if we can look at these values, you can list these out by 10. So this is each day's worth of data, and what we would expect is we have an arrival time and an in-arrival time for every observation, which of course we see here: 281 in-arrival times, 281 arrival time, 276 in-arrival times, 276 arrival times, and so on. So we have our 10 days worth of data, two different observations: the arrival time and the in-arrival time. So one quick thing to note here is that these numbers differ over the day. So we have a random process for the number of customers that come to the food truck, or whatever the arrival system is, and that's certainly what you would expect to see. However, this makes our data not completely rectangular, so that's why I chose in this case to just use standard Python list of lists rather than trying to use either pandas or numpy in this case, is because I have non-rectangular data. Each day has a potentially different number of customers. Okay, so we want to generate histograms, and so I just left this comment for you. If you forget how the histogram works, you can just use the question mark, and that will take you to the help. I'm not going to do that, but that's something you should definitely have a look at to make sure that you understand all of the parameters. So what we're going to do is we're going to create 2 histograms for each one of our individual data components. So we're going to end up with 20 histograms, 10 that represent arrival times, 10 that represent inter-arrival times, and I chose to color each one of these using auburn orange and auburn blue, using the corresponding color code. So I created a subplot figure where I have number of rows equal my replications, which in this case is 10, defined up above. The number of columns is 2, and the figure size is going to be 10 high by 3 times whatever the number, back up a second, 10 wide by 3 times the number of reps. So this in this case will be 30. And then I just cycle through my 2 data sets, right? And I have my all in arrival times in orange and my all arrival times in blue. And also note for my arrival times, I chose to use the bins of size 8 because it's this arrival time distribution that we are trying to get for our arrival process. Remember that when we do the histogram, what it's estimating is this process. And so I wanted that to match the known time window. Okay, so if we execute, it takes a little while. We have 20 plots here. We can now see our individual observations. So you think about each one of these rows represents one of our 10 days of data. The left column, or the orange column, is the distribution of in-arrival times, and the right column is our arrival time. So these are what actually estimate that arrival time, arrival rate process, and they're our primary interest in determining stationarity. So our question that we look at here is, are these observations from the same process? That would be our stationarity from day to day. So I would just, again, make a visual comparison of this data set and this data set and this data set and this data set and say, realizing that these are random samples, so there will be variation, are these samples from the same distribution? If the answer to that is yes, then I would say that the process is stationary from day to day. And so we look at these, and my assessment of this, of course, I already know the answer, but my assessment of this would be that this is stationary on a day-to-day basis. And we also look at the in-arrival times in this case too, and the histograms for the in-arrival times also look fairly similar from a day-to-day perspective. So because of that, I then compute what I'm calling the grand in-arrival times and the grand arrival time data sets, where I just combine all of the data. So I take all 10 days worth of data and combine them into two big data sets, one for in-arrival times and one for arrival times, and then I generate the exact same two plots there. And what we're doing by combining the days is we're smoothing out some of the variation. If it is in fact stationary, then I have valid observations. Instead of having however many I have in one day for each plot, I now have 10 days worth of data. And so in fact you can see our plot here now is looking more and more uniform, like we saw in the data in the figure that I showed for stationary data. And so within the expectation of variability, this certainly looks like it would be modeling a stationary data set. And so this would be a valid representation for that individual inter-arrival time process. So the last thing we do is we use a tool called kernel density estimation. If I was really doing this as part of a simulation study, now that I get to this point, I would want to make an estimate or decide what corresponding distributions to use. And so I just grab the Seaborn tool to do the kernel density estimation that we would actually use if we wanted to actually estimate these processes. So again, I'm not going to talk about the details of that here. If that's something that's of interest to you, then certainly simulation class, as I mentioned before, is what is where you want to go. Okay, so let's go back and take a look at our other data set. So as I mentioned, data set A is stationary. We know that, or I know that. Data set B has a two-phase non-stationary process. So let's just grab that data. Let's look at the values, and you should see these numbers are all similar to what we saw before, because I generated the data such that you have roughly the same arrival rates. And this time when I execute my plots, it's going to take it a second. Again, we have the asterisk there. We can see our distributions on the left, or our histograms on the left, look fairly similar to what we saw. They are actually a little bit different, but if you compared them side by side, you would see a difference. But from an initial visual observation, they look very similar. But our other ones, you start to see the two phases here, right? Within the assumptions of variability, you can start to see a phase here and a phase here and a phase here and a phase here and so on. And so if you compare these from day to day, we again have a process that certainly appears to be stationary from day to day. And because I have that, I can then compute my what I call grand data sets, which again aggregates all of the data across days. And now we can distinctly see that we definitely have a two-phase non-stationary process, where the first 4 hours we have one arrival rate, and the second 4 hours we have a second arrival rate. And then if we then execute the kernel density or do that, you can again see that same characteristic shape. And so finally, our third data set, C here. Let's go back and take a look. Execute C, then look at the values. Again, very similar. Now when we generate, there we go. And now you see more shape. As I said, this is a 4-phase non-stationary process, and so you can see something maybe here and here and here and here. And so this would be kind of akin to what you would expect for our food truck example, where you ramp up in the morning, have a lunch crowd, and then ramp down in the afternoon. Our distributions of inter-arrival times, again, look similar, a little bit different. We're seeing more and more values skewed over here on the near zero than we saw in the previous one. And so we look at the values across days, so day 1, day 2, day 3. The data certainly appears to be stationary from day to day. And then if we assess using our grand data sets, you can clearly see our 4 phases. So I have a 2-hour phase, a 2-hour phase, a 2-hour phase, and a 2-hour phase corresponding to our 8 hours. And so again, kernel density estimation, there we go. Okay, so that's what I wanted to talk about in the module. Again, the idea here was that we understood the issue. The issue was we have an arrival process that we'd like to characterize the stationarity, both from a day-to-day perspective and a within-day perspective. We process the data sets, and then we generated some visualizations that help there. Just as a note, I mentioned several times that I knew exactly what the data was, so this is obviously not actual data that I observed at a food truck. Actually generated the data using a process called thinning that we use to generate the non-stationary process. So sometime I'm going to make a video module on that process, but for the time being, I'll also include that Jupyter notebook here for you to look at, and feel free to contact me if you have any questions about that, if you have questions before I actually make that video.